So in this video, we're going to change from a two-dimensional shape to a three-dimensional shape, from a circle to a cone. And what we want to optimize is the volume of the cone. So on the next slide, we'll sort of show you how can we make a cone from a sheet of paper that's a circle shape. So here we have a circular sheet of paper with a radius of 12. Left and right, they're the same things, just the right-hand side seems to be more three-dimension. Imagine a sheet of paper on a table. And in order to create a cone out of this, we're going to have to cut out a segment or cut out a sector. So imagine me cutting out a certain amount, and that blue part is what I'm going to be folding. But how do I fold a two-dimensional circular sheet of paper into a cone? Well, what I'm going to do right now is I'm just going to take the red part and raise it up. So when I raise it up, what happens? I can just grab this up. So notice how between here to here, I'm sealing in, I'm trying to get the edges, see the pink part there? V to A. I want it to like edge it or make contact with V to B. So I'm gonna have to raise this up. And here we go. We have a full cone. So what happens, and right now we have a three-dimensional cone, and which has a height and a specific radius, because the bottom of the cone is a circle with a specific radius size. So over here, what I'm going to do right now is I'm going to change. What happens if I took cut out a little segment, and the rest of the part was made into a cone? Notice how the cone to the right-hand side gets a little bit lower. The height is lower, but the radius of the base is larger. And if I keep on going around, so I'm going to cut out a lot more. All right, and what happens? Do you see a pattern going on? Yeah, you do. The height is getting more taller, but the radius of the bottom of the cone is getting smaller. And what happens is eventually you're not gonna get a cone when you have nothing to fold. So as you can see here, it's very, very tall, it's very, very steep. But the radius, when you take that blue sector and fold it, the circle at the bottom of the bottom is really, really, really small. So because we are maximizing the volume of a cone, we're going to have to find the equation. So let's write the equation of a cone, which is pi r squared h divided by 3. So when you want to find the volume function, which you're going to optimize, take the derivative of, you have a choice v of r, v of h, or maybe v in terms of another external variable. So let's have a look at the dimensions of this cone here. We know that the cone here has a height and a radius. So in this case, we'll call this h and this r. And if you notice in this h and r, we have a right angled triangle right over here. All right. Now we have to figure out how this cone is made. Well, this cone is made from a sector of the circle. Now we know that the pink part here is the radius of the circle, which is 12. That has been provided for us. Now, if you can imagine this part here, there's a lot of connections of the 2D. So imagine the yellow part here. So yellow part is the arc length. Okay. Now the arc length, when folded into 3D, will become the circumference of the base of the cone. That's number one. Number two, this 12, this radius of the 2D, will become the slant of the 3D. In other words, this pink part, which I'll use red, is going to be 12. So if you can see here, we have a constraint, because no matter what happens to the shape of 2D, let's just say you cut it out less of a green part, what's going to happen is that nothing's going to change in terms of the pink part. The pink part will not change. The only thing that will change is the height and the radius. But no matter what happens, the Pythagorean theorem will be the constraint connecting the h, r, and 12. In other words, our constraint is h squared plus r squared is equals to 12. So now we have a choice to express the function in terms of h or r. In this case, this is where you have to be sort of, it's up to you. But for me, I'm going to isolate for r squared. Why would I isolate for r squared? Because I already have an r squared here. In other words, I don't have to take the square root on both sides. I can just sub in this entire piece into the red part here. So in other words, I'm going to express v in terms of h. Okay, so we have pi over 3. This r squared is, I'll put the h first over here, and then I put in bracket the r squared, which is 12 minus h squared. In other words, my function here is going to be, I'm just going to expand the bracket part, 12h minus h3. So I have a cubic function. Now, miss, can I not express it in terms of v of r? Yes, you can, but you're going to have square roots involved. And that's going to make the derivative a bit more challenging because you're going to be using chain rule and more complicated factoring to solve for the zeros. So before I move on to restrictions for h, I made an error. We're going to have to put a 12 square, 12 square, 12 square, and we'll just make this 144. So after this, we're going to have to find the restrictions, meaning for h, meaning h is going to be positive, all right? But if you didn't know that, but one thing you should know is that the volume must be greater than 0. So we're going to be solving inequalities in the next slide to solve for the restrictions of h. So here we have the function for volume, and then I'm just going to factor this because I can see that this is a difference of squares in that bracket part. And then afterwards, I'm going to set up the charts over here. And then I know that the h could be equal to 0 and the h is going to be equal to 12. There's no point in h being negative 12, so here are my intervals, okay? And then we know that this area is not acceptable. And then I'm going to set up my parameters. So we have pi over 3, h, 12 minus h, and then 12 plus h. And then I just do all the signs. And based on this, I know that if I subbed in, for example, h is equals to 1, that's a positive, 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 and a positive, it's a positive. So this is the zone I do want. But if I sub in a number, for example, h is going to be, for example, like 20. So this piece here will be a positive, positive. 20 here is going to give me a negative. 20 here, 20 plus h is going to be a positive. Negative, I do not want this zone. So I know my restrictions are going to be between 0 and 12. So now let's figure out the critical numbers and critical points. In other words, I'm going to take the derivative. The pi over 3 is just a constant, it stays. And then I'm going to take the derivative of the inside, which is 144, using the power rule, 3h squared. I'm going to set it to equal to 0. And this is my source of my critical numbers. In other words, I'm just going to bring the 3h squared over the equal sign. And then I end up getting 144 divided by 3, which equals to h squared, and then I'm going to take the square root of this, and that's become 144 over 3, which equals to h. And that becomes root 48, and let's just rationalize this, make it into mixed fraction. This becomes 4 root 3. So I want to make sure that this is a local maximum, so we're going to have to show it's a local maximum. So I'm going to use the second derivative, so I'm going to take the first derivative, which is here. Take the second derivative, so I'm going to just leave the pi over 3 and take the derivative of the bracket inside here. That becomes negative 6h. So then I'm going to sub in my 4 root 3 inside here. And what's going to happen without even using a calculator, I'm going to get a negative number. So I know it's going to be concave down. It is therefore a local maximum. So this critical point here, I'm not going to check the y value or the dependent variable because I know it exists. It's a local maximum. So the last thing we're going to verify is whether this local maximum is the absolute maximum. Is this number here the maximum value that will give the volume of a cone? So in other words, we're going to have to check the actual volume. So we're going to figure out the volume of root 3, and all we're going to do is sub it into here, the top part here. We end up getting the following: root 3, 144 minus this becomes 48. And then you can simplify it and you get a number. I'm not going to bother with using the calculator. But the other hand, we have to figure out the endpoints. Let's not call it endpoints, it's called the end behaviors. In other words, we need to figure out the limit as the height approaches 0 from the right-hand side of v of h, and versus the limit of the height being close to 12 from the left of v of h. And all you have to do is simply technically take the 0, sub it into the function here, and you end up getting 0. And here, you also end up getting 0. And we know that this number here, which a number it will exist because I can see that it's going to exist, is going to be the largest absolute maximum. So here we found out that the height, the ideal optimal height, is 4 root 3. And we need to address the original question. The question asks, what is the sector that you're going to cut out to make a maximum, to create the maximum volume? So we're going to have to work backwards and figure out the angle of which it's been cut out. So keep in mind, if we have the h ready, we can work backwards and figure out the radius using Pythagorean theorem, and then we can calculate the circumference of the base, which is the arc length of the sector. So let's actually do one thing at a time. Let's figure out the radius. In other words, h squared plus r squared is equals to 12 squared. R squared is equals to 144 minus 48. I just squared this number here. And that becomes r squared is equals to 96, and I'm going to just sort of take the square root of this 96. That becomes I believe it's 4 root 6. So now the next thing we're going to do is figure out the circle part, the radius. I'm going to here, I'll use green. So this part here is the circumference. So circumference, I'll use green here. The circumference of the cone is equal to the arc length of the 2D circle. And the circumference of the cone is going to be 2 pi r. And we know the radius because we actually calculate it to be, in this case, is going to be 2 pi times 4 root 6. And that will become 8 root 6 and pi. So this here is the circumference and also the arc length. So this piece is also your arc length. Now the second last thing we're going to do is we need to calculate the angle. So I'm going to call this theta. And there's a connection between the angle and the arc length and the sector. And if you call it advanced functions, there is a proportion. All right, when you learned about arc lengths. All right, and in this case, the arc length is equals to r theta, and r is the radius of the 2D circle. We have the arc length, let's figure out the theta in radians. So everything will be in radians. So in this case, theta is going to be arc length over radius. In this case, arc length is 8 root 6 pi, and then our radius of the 2D is going to be 12. This is in radians. And if we change it to degrees, since we can imagine what degrees is, we're going to multiply by 180 divided by pi, and that will give us, it's going to give us 294 degrees. So this piece here that we're maintaining is 294 degrees. And if we want to find out the leftover piece, the piece that we're going to cut out, so this area here, so this sector here, I'll put here red, let's find out this sector, let's call it alpha. In other words, alpha is going to be, and we know that this is going to be 294 degrees, so we know that the full circle is 360, so 360 minus 294 degrees is going to give us 66 degrees. So in conclusion, the ideal piece to cut out is to make the largest cone is to cut out a sector that has a 66 degrees, and then you'll get your maximum cone.